Got this on video?
Yeah.
Okay, cool. So what we've got is a capacitor and an inductor and a light bulb, and what we're seeing is the output of them on the oscilloscope. And what we notice is that as we turn up the voltage, as we turn up the frequency, we see the amplitude of the wave here. This wave's the resistor voltage that we're measuring here. We see that as we turned up the frequency, the amplitude of that wave went down, the light bulb went out. And so what we're seeing is that at high frequency, the current dropped off to zero. And we can turn the frequency down again and see the amplitude of that wave growing. We go down, 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 and down, 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 down. And then as we get to low frequencies, we can see once again that amplitude's starting to compress up, and that once again the light bulb's gone out. So what we're noticing is that by having a capacitor and an inductor connected up in series, we've created a tuning circuit. So at a certain frequency, current flows and the light bulb glows, but when we're below that frequency or above that frequency, current doesn't flow.
Oh yeah, I've been filming since the Land Rover episode.
Oh no, this is going to be embarrassing. Okay, so these Lrc circuits, what we're doing is we're connecting up the inductor and the capacitor with the resistor, and we're playing off the fact that inductors have a really high reactance when the frequency is high, because they respond to that high rate of change of current through the circuit, and the fact that capacitors have a high reactance when the frequency's low, because they charge up more when the frequency's low, because more charge flows in one direction when the frequency's lower. And that means that the circuit is going to have a sweet spot at which it will resonate. And we can understand that by having a look at a phasor diagram. So over here, the circuit's not resonating. We've got the resistance poking out to the right, we've got an inductance leading. The inductance phasor there is smaller than the capacitance phasor. And so to work out the impedance of that circuit and where the supply voltage sits relative to the resistor and thereby the current flow in the circuit, we can draw the inductance phasor, or draw the smaller of the two phasors, nose to tail, on the longer of the two reactance phasors. So we can kind of dotty our X out in there, because what we're doing is we're going the XC and we're adding on the XL to it, because they're vectors and they're 180 degrees out of phase. Phasors, they're 180 degrees out of phase. Adding them together is kind of like subtracting, and so we can represent that with a new phasor. XC minus XL, and so that represents the reactive component of the circuit. And so then when we're trying to find what the overall impedance of the circuit is, we can see that it's going to poke out over there. Interesting points are that the capacitor voltage, the reactance of the capacitor, and thereby the capacitor voltage, is greater than the impedance and therefore greater than the supply voltage. So it's totally possible when you're doing Lrc circuits that you get the voltage across either the inductor or the capacitor can be greater than your supply voltage. It's not something to worry about if you think that you've made a mistake. The impedance in this situation something like that. It's going to be just using Pythagoras, the square root of r squared plus xc minus xl squared. Obviously, the order of the xc and the xl matters there because we're subtracting, and so we just have to think about which of our phasors is greater. It's always the greater one minus the lesser one is the order of subtraction in that bracket there. And so that's how we think about an LRC circuit. The phase angle, as before, sits between the resistor, that's in phase with the current, and the impedance, that's in phase with the supply voltage. And so that circuit's not at resonance. If we were to bring it to resonance by adjusting the capacitor, and usually it is the capacitor, we twist the knob on our manual radio, it's usually a capacitor that we're tuning. It's one of those ones that have leaves that kind of move in and out, and by changing the area of overlap of the capacitor plates, that's how we're adjusting the capacitance of the capacitor.
You know, it'd be cool, Steve, if you had elevator music playing as you sped up the new drawing and writing things.
And so, when we bring that circuit to resonance, you can see we've reduced the XC phasor from where it was down here to here. And so now, when we draw the XL next to the XC, we can see that those two are going to exactly cancel each other because they're 180 degrees out of phase. And so what we can see is that at resonance, it happens when the reactance of the inductor is equal to the reactance of the capacitor, and that forces the impedance of the circuit to be just equal to the resistance. And that's the smallest value of impedance that we can ever be. Smallest impedance, greatest current flow. And so let's just work this through. So that's on your formula sheet, and that's how you derive it. F naught is just the symbol that we use for the resonant frequency as opposed to any frequency. So I guess the last thing we need to think about, got all of that. The last thing then is what happens if we plot up our current flow as a function of frequency. We can start by just dotting in the resonant frequency. And what we see is that when we're away from the resonant frequency, the impedance is large because either the reactance of the inductor is large or the reactance of the capacitor is large. And that means that our current flow is going to be low. So over here, low current flow, and it gradually increases, but then really peaks at that resonant frequency. There's a really narrow peak, and then kind of does the opposite on each side. And so why this is really useful for us is that we're going to get a really distinct maximum current flow, maximum resistor voltage at one particular frequency. So this is really useful for tuning a radio in to a particular frequency. When we turn the knob on our radio, we adjust the capacitance of the capacitor, and that adjusts the resonant frequency of the circuit. It moves this F naught up and down the frequency band, and we see that line moving up and down on like the tuner thing on our radio. And when it finds a signal, it amplifies that signal that it finds. We get a maximum current flow like at that frequency. We hear just that signal, not all the bajillions of different signals that are being broadcast. Is that sort of... Anyone got something they want to say?